Hi, everybody. It's my pleasure to introduce today's colloquium speaker, Ellen Zweibel. Ellen is an astrophysicist and plasma physicist who has worked on some of the most exciting aspects of astrophysical plasmas. Her work spanned the energetics, dynamics, and stability and scales from the stars to clusters of galaxies. Ellen received her bachelor's in mathematics from the University of Chicago and her PhD in astrophysical sciences from Princeton. She was then a postdoctoral fellow at the Institute for Advanced Study before she joined the faculty at the University of Colorado Boulder, where she spent a large fraction of her career. She then moved to the University of Wisconsin-Madison, where she serves as the William L. Krashauer Professor of Astronomy and Physics and the Willis Distinguished Achievement Professor. Ellen is also a member of the National Academy of Sciences. Today, she's going to tell us about the foundations and phenomenology of cosmic ray feedback. Ellen, please go ahead.
Can everybody hear me? Okay, so I'm delighted to be here. I want to begin by acknowledging my collaborators, both past and current. My goal, just like people who want a license plate from every state in the union, is to have someone from every letter of the alphabet at least once. So, and let me also say at the outset that both astrophysics and plasma physics are just notoriously jargon-laden. And if I say anything that just could be clarified, please don't hesitate to ask a question. Okay, so to set the context, the sort of big problem that we're interested in is a problem that's really central to the formation and evolution of galaxies, namely what determines gas content, the rate at which stars form, and how the galaxy interacts with its environment. And feedback is the idea that these processes are inherently self-regulating. And the primary engine for this is really stars. There's also supermassive black hole feedback, but I won't talk about that today. And the stars inject energy in the form of radiation and winds during their lifetimes, and then as supernova explosions, the massive ones. And these things together pressurize the interstellar medium, which I'm going to abbreviate in this way. And that staves off gravitational collapse. It drives so-called fountain flows, which leave the plane of the Milky Way and then come back, and actual outflows, which don't come back. Now, it's estimated that about 10% of stellar energy output, primarily during the supernova phase, most likely, is channeled into cosmic rays. And a major objective of our program is to understand why and how cosmic rays are really much more than a 10% effect in feedback. And though I won't be talking about these other systems here, let's see at my, okay, I won't be talking about these other systems, but the physics that I'll be talking about is relevant way beyond galaxies, back to cosmic rays. So, okay, so to kind of sharpen the context, right, the easy part, the hard part. So the easy part is, in some sense, it's just the process of elimination. So supernovae heat gas to very high temperatures. That gas rapidly radiates away its energy, and it's not very effective at driving outflows. Radiation is an attractive mechanism, but it's vulnerable to leaking out through low-density pathways, can't carry a lot of material with it. And the energy that goes into turbulence dissipates in shocks, which are very compressive and radiative. So harder part is figuring out how cosmic rays could actually do it. So they're an essentially collisionless species, and in order to be agents of feedback, they have to exchange momentum and energy with the interstellar medium. Interstellar medium is magnetized, which of course is how it happens. But in order to really understand that these processes at a fundamental level, you need to go all the way down to kinetic scales, the gyro radius of the cosmic ray, or even below. And then we have to translate that into a prescription that's useful global scales, which are separated from the kinetic scales I'll show you later by about 10 orders of magnitude. This is a multi-scale problem par excellence. Okay, so the plan of this talk is I'm going to go through just a couple slides, the salient properties of cosmic rays, interstellar medium, and a little bit of plasma physics and magnetohydrodynamics. So don't blink. And then I'm going to give a little review of transport theory. And the focus of this is going to be characterizing how cosmic rays exchange momentum and energy with the thermal gas, and how we can derive a fluid theory that accounts for this. And then I'll show some results and phenomena that are interesting here. This is obviously a very active field, as you can just tell from the number of people at this workshop, which is only a subset. And I cannot possibly do justice to all the great work that's being done. And so I did a cut based on early career researchers. So I'm not going to be complete there either, but that was my one of my criteria. Okay, and then I'll just summarize and say where I think we are. Okay, so properties of cosmic rays. So I'm showing two different views of the cosmic ray spectrum. You can see that it extends over many orders of magnitude in energy. I like this image because it's very simple and it shows you the challenges of detecting particularly highest energy cosmic rays. This can only be done with very large arrays. I like this image of the spectrum because it has more in it, and you can also see the vast number of experiments that have gone into making this spectrum. You can see that the electrons are down from the protons by a couple of orders of magnitude. Positrons, which we believe are secondaries, antiprotons, which we believe are secondaries, are down even lower. And most of the energy in cosmic rays, which is what's important for their fluid effects, their pressure and their energy density, is at the lower energies, a few GeV to maybe 100 GeV. These their deviations from a consistent power law are known as breaks in the spectrum, knee, the ankle, and so on. And I'm not going to talk about what might produce these and changes in composition, possibly changes in acceleration or propagation mechanisms. I'm really going to be focused on the cosmic rays that account for most of the energy and pressure. So there are a couple of useful pieces of information that are important for deriving this fluid theory. The first one is that cosmic rays are extremely isotropic in arrival direction. We can't measure this at the lowest energies reliably because they're interfered with too much by the magnetized solar wind, but you can see that at, the anisotropy is down at the 100th to 10th of a percent level. The other thing I want to discuss is the so-called boron to carbon ratio. Okay, so to unpack this a little bit, carbon is made in stars. It's a fairly common element in the interstellar medium, and boron is not made in stars. It's actually destroyed in stars. So the boron, and it wasn't made in the Big Bang either. So the boron in the universe comes primarily from so-called spallation reactions between carbon, nitrogen, and oxygen nuclei, cosmic ray nuclei, and interstellar hydrogen. So that it fragments into energetic nuclei and leading to a wildly overabundant action of boron in the cosmic rays. That's also true for lithium and beryllium. And from the boron to carbon ratio, we can calculate how much material cosmic rays have passed through between their acceleration and their arrival and detection at the Earth. And we can use these two pieces of information to put together a story where cosmic rays are confined in the Milky Way for of order 10 million years, maybe a few million years, maybe a little bit more. the confinement time actually decreases with increasing energy. And the reason that they're confined for much longer than the light travel time through the galaxy is that they're trapped by the galactic magnetic field and they scatter then it. I'll be fleshing that out. Okay.
One question that we
Yes.
brought over anisotropy that in higher energy region you have a factor in phase over anisotropy. Should I take this seriously or?
Well, you mean this feature here?
Yeah.
Yeah, you could take it seriously, but I'm not going to talk about it. I think, I mean, the whole problem of where these, so once you get, sort of into this region, these cosmic rays are arguably not confined by the galactic magnetic field because their radius of gyration is bigger than the galaxy, comparable. So they're extragalactic in origin, and this is probably saying something about their sources. But let's go into that later because it's, yeah, but yes, do take it seriously. Okay. So cosmic rays gain most of their energy over a short amount of time. Why do we think that? We think that because the boron to carbon ratio decreases with increasing energy, implying that the confinement time in the galaxy is shorter. But if they were continually gaining energy, we would expect the most energetic cosmic rays to also be the oldest. And they're not. They seem to be the youngest. Shocks driven by young supernova remnants are the favored source. You need about 10% of the supernova energy that does not come out in neutrinos, so 0.1% of the total energy. That's about what you need to keep the cosmic ray pool in a steady state. And because of the isotropy and the confinement time, they're well scattered. I'll depict in a sketch how that might happen. And it's really only because of this near isotropy that we have any hope of driving a fluid theory. As I'll make clear. Okay, so if that was a glance, this is a squint. This is the interstellar medium. Here's a multi-wavelength view, gamma rays, X-rays, optical, infrared, and radio. This is the Faraday sky. So we don't know how far away this stuff is. This is galactic coordinates. The blue and the orange represent different directions of the magnetic field component along the line of sight. You can see that there's large-scale order, but also many small-scale features. The interstellar medium has a vast range of densities, temperatures, ionization fractions. It's turbulent. The magnetic field also varies. This is a reconstruction from data of a sort of face-on view of the magnetic field above and below. And as I indicated before, the engine that drives all this is primarily the radiation winds and explosions of massive stars. And gas kind of cycles in and out of the interstellar medium over a few tens of mega years. So just as all the cells in our bodies are replaced every 7 years, interstellar matter, it's also kind of it's coming in, it's going out, it's being incorporated into stars, it's being ejected from stars. It's never the same. Okay, that was the interstellar medium. Now let's do plasma physics. Okay, so magnetohydrodynamics is plasma physics on long enough length and time scales that kinetic particle effects can be ignored. So in particular, we don't resolve the gyro radii of plasma species. We don't solve the Debye length and so on. An important dynamical parameter is the ratio of plasma to magnetic pressures. This is called the beta parameter. It's about 1 in the interstellar medium. It's more than 10 in clusters of galaxies. And a sort of fundamental entity in this talk will be the so-called Alfvén wave, which is basically the low frequency limit of electromagnetic waves. And you can describe it within the framework of MHD as driven by a magnetic tension. So just as sound waves are driven by pressure, Alfvén waves are driven by magnetic tension. And so if you bend a field line like so, restoring force is as indicated by the arrows. And the characteristic speed of propagation is the Alfvén speed, which is a vector quantity magnetic field divided by the square root of 4 pi times the mass density of the charged component, whatever that might happen to be. Okay, so how do we describe all this theoretically? So here is an image of a spiral galaxy at 51, showing the general kind of spiral orientation of its magnetic field. It's superimposed on radio continuum brightness, so you can see spiral arms. It's a nice face-on spiral. You can see the general spirality of the magnetic field. And here on the right is the circle represents a gyro radius of a typical cosmic ray. And this black line here is about the Sun-Earth distance. And the scale of separation between this and this is about 10 orders of magnitude. And so, since the gyro radius is proportional to the energy of the particle, you really have to get up to EeV energies before you can resolve out the small-scale structure that you saw on the map. So we think that the way cosmic rays travel through the interstellar medium is that they're pretty well tied to field lines, which themselves have some irregularities, and they scatter up and down along field lines. So their rate of diffusion is somewhere in between what the magnetic field itself is doing and what's dictated by this relatively short free path. Okay, so what is the nature of this dynamical coupling? So perpendicular scales, it's sort of easy. So cosmic rays have no inertia. And so in a steady state, the gradient of their pressure perpendicular to the magnetic field is their current crossed with the magnetic field itself. The Lorentz force on the thermal gas has the same form. It's the current in the gas. Fortunately, we don't have to know the cosmic ray and gas electric currents individually, because we know that their sum is related to the magnetic field itself through Ampere's law. We know that the current on the gas is the total current minus cosmic ray current. So we can replace the Lorentz, the thermal gas current with the total current and use Ampere's law and the cosmic ray pressure gradient. So it looks a bit like a sleight of hand, but it kind of shows how perpendicular to magnetic field lines cosmic rays can make their pressure felt in the interstellar medium. Yes?
A really, really dumb question, but
There are no dumb questions. Yes.
what is the sort of this magnetic field like?
What's the origin of this magnetic? So I think it's one of the unsolved problems in cosmology. I have another colloquium on it, which I won't attempt to give. It's a great question, not dumb at all. Okay. So in addition to where the magnetic field comes from, there's this subtlety on how cosmic rays make their pressure gradient felt along the magnetic field. And I want to begin by introducing what's the traditional picture, which involves a process called gyroresonance scattering. And the basic idea is this: if you have, so this red here is a field line and it has large scale curvature and tiny scale wiggles. And the black helix is the gyro orbit of a cosmic ray. And these tiny scale fluctuations, tiny with respect to the gyro radius, kind of average out over the orbit. And you follow the large scale field pretty closely. But just as if you're riding your bike, you can ride over washboard, go up and down hills. But if you encounter a trench that's approximately the width of the separation of your wheels, you will interact very strongly with it. You will be scattered. Similar analogies for surfing and skiing. And mathematically, you can describe gyroresonance like so. So if we have a wave with some frequency omega, wave number k, This is the parallel velocity along the field. So this is the Doppler shifted magnetic field, fluctuation magnetic field that the particle sees as it gyrates. And if it completes one gyro orbit in exactly one parallel wavelength, satisfies this condition, and it is resonantly scattered. And we can estimate the scattering frequency in the following way. So the field line fluctuation makes some angle, delta theta, with a mean field, and the change in angle, this mu, will be of order delta theta itself. And if we assume that we have many uncorrelated waves, we can construct a scattering frequency based on random walk arguments. And if we set the frequency of encounters to be the gyro frequency, we come out with this expression. So it's quadratic in the fluctuation amplitude and proportional to the gyro frequency, the relativistic gyro frequency of the cosmic ray itself. In addition to changing its pitch angle, the relationship between perpendicular and parallel velocities, it will hop to a slightly different field line. And the amount by which it hops is of order its gyro radius scaled by this delta B over B. And this leads to some perpendicular diffusion, but it's much, much less than the parallel diffusion up and down the field. And we can explain the boron to carbon ratio and the anisotropy if delta theta is order 10 to the minus 3, or cosmic rays in the GeV range. Okay. Now, where do these fluctuations come from? So here's the first divergence in the theory. There's a so-called self-confinement theory, which was developed in the 1960s. And the idea for self-confinement is that these waves are actually generated by the cosmic rays themselves through a kinetic scale instability, which I'll describe. And the alternative theory is that the waves are there as part of a turbulent cascade. The interstellar medium is turbulent, and some fraction of that turbulent energy will cascade down to gyro radius distances. I'll be focusing mostly on this picture, sort of this classical cosmic ray hydrodynamics, but I'll talk a little bit about this one as well. Okay, now before going any further, I want to highlight the fact that this picture may not be the correct one, given what we now know about HD turbulence under interstellar conditions. So here are 3 realizations with different fluctuation strengths, simulations of driven turbulence in boxes. And the magnetic field has these highly folded structures. It's really hard to visualize this as a collection of randomly phased small amplitude waves. And although the gyro scale remains an important scale for scattering, really, so you can kind of cruise along the straight field line for a while, and then whoop, you go around the bend, and what happens? And we don't yet know, but I think we will know pretty soon, how cosmic rays exchange momentum and energy with these folded structures, which is, after all, what we're trying to get at. So this part of the field is really very much under development. So going back to the theory that we understand, it came about in the following way. It was developed back in the 1980s by Heinz Fulk and his collaborators. And they were primarily interested in how cosmic rays are accelerated in shocks. And since this is thought to be the dominant mechanism of cosmic ray acceleration, I thought I would very quickly tell you how it works. So this is in the rest frame of a shock. It's in that frame, unshocked fluid is moving in, and shocked fluid is moving out more slowly. And if a particle scatters, say, from the shocked side, the unshocked side, it will pick up some energy that's proportional to the speed of the shocked fluid. And then if it comes back across the shock, it'll overtake the fluid, in a sense, the scattering center in the fluid, and it'll lose some energy, but it won't lose as much as it gained because this fluid in the shock frame is moving more slowly. There's a net energy gain loop, and this is an example of the so-called first first order Fermi process. And it can now be simulated very successfully. This is just one of many simulations from Anatoly Spitkovsky's group. So the fluid theory kind of went in here. It was a theory that went beyond a test particle theory like this, but not an attempt to do a full kinetic simulation. These equations have turned out to be incredibly useful. So they're based on this so-called streaming instability. So let me go into that a little bit. I've written down the growth rate in full glory so you can see where the pieces come from. This is the condition. So this is an integral of the response of the cosmic ray distribution function to the electric and magnetic fields in the wave. In this delta function is encoded the resonance condition. This says that only resonant particles play a role in amplifying or damping the wave. F, you saw that the cosmic ray spectrum decreasing function of energy. So this term is generally negative and will damp the waves. But this term, so this kV over omega here, P is essentially the speed of light. Omega over K is the Alfvén speed. So this multiplier, the anisotropy, is very large. And what that means is that the anisotropy only has to be of order VA over C, overcome the damping and destabilize waves. Unfortunately, there's a simple approximation to this expression, which says that it's scaled by the ion cyclotron frequency, the ratio of cosmic rays that can resonate to the thermal ion density, times the drift associated with anisotropy divided by the Alfvén speed minus 1. So VD over VA equals 1 is actually the exact marginal stability condition.
What is U then?
What is, sorry, which? U. Oh, that was V parallel over V. That's the cosine of the pitch angle. Okay. So you can go back now and calculate scattering rate due to these many encounters. So this was the, sort of heuristic geometrical argument that I went through with you before, but now on a more formal footing. So F naught is the unperturbed distribution function. And what this measures, this is the average change in the zero-order distribution function caused by wave fields interacting with the perturbation to the distribution function. And this absolutely miraculous thing happens, which was first shown by Kennel and Engelmann back in 1966, that if you put in how F1 relates to E1 and B1, you actually get a diffusion tensor in momentum space. How lucky is that? The biggest term in this diffusion tensor is pitch angle scattering. And the scattering frequency is indeed of order what we estimated. And the other components of the diffusion tensor are smaller than pitch angle scattering. Basically, they represent diffusion in magnitude of momentum. And since the electric field is down from the magnetic field by of order VA over C, they're small. Okay. We can use the Fokker-Planck equation to derive an energy equation, which is multiplied by particle energy, integrate over momentum space. So here is the cosmic ray energy density. It says that the time rate of change plus the divergence of the energy flux, cosmic rays. So far, this is kind of what you get in hydrodynamics. But then you have this sort of mystifying looking integral over the right-hand side. I is the intensity in the wave. 2 gamma is the rate of amplitude change. And so in order to evaluate this, you would actually have to know what I is. So the right-hand side at this point doesn't look very useful. But if we make the assumption that cosmic rays are frequently scattered, the short mean free path, you can relate the anisotropy. So I've written it here, allowing for energy change, in terms of the spatial gradient. And if we put that into the components of the diffusion tensor, we reduce it to this extremely simple and nice form. So now what appears on the right-hand side looks like a sort of frictional heating, representing the friction of a cosmic ray fluid moving at the Alfvén speed relative to the thermal gas. But if you kind of look under the hood, what it really represents is energy transfer to the Alfvén waves. Okay, we can derive an equation for the waves, which based on WKB theory, which I'm not going to use. And I'm going to talk about how we actually determine the parameters in. So we need to know not only about excitation, but also about damping. And the three damping mechanisms which have received the most attention are friction between the plasma component and the neutrals, which don't feel a wave directly. This is important in the neutral phases of the interstellar medium. A process called nonlinear Landau damping, whereby thermal ions undergo a resonant energy transfer with wave packets. This is important in the hot, fully ionized medium. And then the newest of these mechanisms is the distortion of these wave packets by interactions with the background turbulence. This mechanism has actually recently come under siege. And it's one of the things that I'm working on in this 2-week period. Okay, so if we balance growth rate against whatever damping rate is important, that kind of tells us how big V drift has to be. And V drift is not too large for cosmic rays with energy kind of in this range, below a couple of 100 GeV. And then above that energy, so those are the large gyroradius particles that interact with long wavelength waves, and there just aren't enough of them to really balance damping unless they're extremely anisotropic. And so the shorthand for this is to say that self-confinement works below this kind of characteristic energy. We have enough cosmic rays to scatter the particle. Okay, so this is the fluid treatment. The cosmic rays stream down their pressure gradient at the Alfvén speed relative to the thermal gas. They transfer momentum through their pressure gradient. They heat the gas at this minus VA dot grad PC. They diffuse with a diffusivity determined for marginal stability. If we said that the waves were instead due to extrinsic turbulence, we would leave out the streaming and heating, but we would retain the pressure force. And this has been applied all over the place. Okay. So although it was originally derived as an analytical theory, there's been a lot of progress in numerical approaches. So full particle and cell, this is full kinetic modeling. I showed you an example of that for diffusive shock acceleration. Acceleration of ions can be looked at through called hybrid simulations with kinetic ions and fluid electrons. And there's MHD hybrid, which actually really like, which you treat the thermal plasma as a fluid and the cosmic rays kinetically. This is receiving a lot of attention. And then there's just the fluid treatment, where you just work with these hydrodynamic equations, and they're typically useful for global models and other large-scale models. Okay. So now I'm going to talk about some examples of the theory in action and how transport really matters. So here's some work by a student in my group, Mark Hobiger, and the idea. So this is the same physical situation under different transport models. So the idea is that here's a stratified galactic disk. Here's part of its magnetic field. We inject cosmic rays in a small volume, and then their pressure pushes gas out of the tube and kind of blows this bubble in the magnetic field. And the reason this field is buoyant is so initially the buoyancy gets going because cosmic ray pressure pushes gas out the sides of the box. Then once the field line rises, this gas streams down it under the influence of gravity, and that accentuates the buoyancy process. So in the column on the left, this is kind of the limit of no diffusivity and no streaming. The cosmic rays are just advected with the gas. On the right, we put in the kind of classical cosmic ray diffusivity. Again, you get a big response, although it's not exactly the same as this. This is pure cosmic ray streaming with no diffusion. And although it's going in the same direction, it's a much slower process. So a first attempt to account for the fact that the densest gas in the galaxy is weak. This was work led by Ryan Farber about 5 years ago. And here are mass loss rates, and sorry, these are star formation rates under 3 different assumptions about transport. So here's what happens if the cosmic rays are just stuck in the gas. This is a model in which they diffused at the same rate throughout the medium. And this is a model where, to reflect the fact that ion-neutral collisions are very effective at damping the wave, diffusivity is larger in cold regions. You can see that if the cosmic rays are stuck into the gas, they suppress star formation very effectively, very effective cosmic ray feedback. And why does this happen? This happens because they contribute some pressure to the gas and prevents it from gravitationally collapsing. And there's very little wind here. These lines here represent galactic wind. Under diffusion, they do diffuse out of the dense regions, leading to less effective suppression of the star formation rate and a little bit more of a wind. And in this case, they simply leave the dense gas behind. You get almost the same star formation rate you would if cosmic rays were not present. And you do drive a wind, but it's a very low density wind with a very small mass. It's just a low density, fast wind. So time has gone by, not that much time actually, and there's some very sophisticated models out here. So here's some work led by Lucia Armilata from Eve Ostreicher's group. And this is a simulation of outflow driven from a tall box using HD, cosmic ray streaming, and diffusion, calculated assuming that ion-neutral friction is the dominant damping mechanism in cold gas, and this nonlinear Landau damping process is the key process in the warmer, fully ionized gas. And I've done this oval here because here near the galactic midplane, you can kind of see how everything relates to everything feature by feature. So there's low density gas, high density gas, cold gas, warmer gas. You can see what's flowing. You can see what the alphane speed is. You can see, what is this column here? Yeah, this is 1 over the diffusion coefficient. So this represents a really large diffusion coefficient in the cold gas, a smaller one in the hot gas, cosmic ray pressure, and cosmic ray energy flux. And this has been followed over very long times. We've also entered the era of global simulations. So this is work led by Timon Thomas from Christoph Frommer's group. This is a global simulation of galactic disk. Similar physics to what you saw previously, except that the damping mechanism is all nonlinear Landau damping. And we just see this wind being driven out of the plane. Okay. And then here's some work by Rourke Habiger, a student in my group. So this is actually the image that he made to advertise this talk. So this shows cold gas, tall box simulation, cold gas in the plane of the Milky Way. This is a temperature map. You can also see the magnetic field lines. They're being buoyantly elevated. What's happening here is that source injections are happening probabilistically at star formation rates similar to the Milky Way. This is the integrated cosmic ray pressure, and this is the cosmic ray pressure along the face. And the reason I included this figure is that it shows what that 10% in cosmic ray energy does versus just leaving it all in thermal energy. So in cyan, you see the the outflow. This is over time. We see the outflow, and then we see the inflow. If we include cosmic rays, we get this big spike here. And this spike actually represents the action of an instability called the Parker instability. So cosmic, that 10% really matters, and more than the 10% level. Okay, so flush with success, I want to talk about a final topic, and that is the inherent self-limitations of the self-confinement. And what it springs from is that if we can ignore diffusion, if the cosmic rays are really well coupled to the gas, you can show that their pressure divided by the gas density to the 2/3, which is half the adiabatic index for a relativistic fluid, is constant along magnetic field lines. And this is basically what you expect for fluid streaming at the alphane speed. Remember, the alphane speed is proportional to 1 over the square root of the density. So when the cosmic rays and the thermal gas have aligned density gradients, they're both negative along magnetic field, this all makes sense. As you progress along the field line, gas density is going down, cosmic ray pressure is going down, and the anisotropy is in the direction of streaming, and the unstable waves are propagating in the direction of streaming too. But nobody says it has to be that way. So what if gas density gradient suddenly changes sign? Well, that would imply, if we keep this invariant, that the cosmic ray pressure gradient also changes sign. So the cosmic ray pressure is going up. And then the cosmic rays are streaming up their pressure gradient. And the theory that we developed predicts that those waves that are streaming in that direction are damped, and the others are excited, but they aren't any going that way. So what happens? So this is the so-called bottleneck phenomenon. And it's not just, perverse thought experiment. For example, in galaxy clusters, these contours represent density gradients. We know the magnetic field is pretty tangled because the radio polarization is fairly low. So field lines will kind of dip up and down the density gradient. And cosmic rays streaming along the field lines will sometimes be in a region of co-alignment and sometimes anti-alignment. So what happens? So we worked on a much simpler problem. Josh Wiener was a student of Peng O. We later worked on this with Mateus. Chad Bustard, a former student in my group, worked on it too. We started with a much simpler problem, which is, let's assume there's a cosmic ray source here, and there's a ionized cloud that's threaded by the same magnetic field lines as the cosmic ray source. So Josh did a set of one-dimensional integrations, and what we found is that on a time scale that's about the alphane travel time between the source and the cloud, you establish these cosmic ray pressure plateaus. Here on the left, if you have no cloud, over time, so 6 megayears is about the alphane transit time, and that should be invariant. So cosmic ray energy density, cosmic ray pressure, they're basically the same, divided by 1 over the density to the 2/3. This is really approaching a constant. It takes a few million years in this case set up. And what happens in the case with cloud, so the density goes up, the alphane speed goes down, is you get this cosmic ray pressure plateau. So there's a jump in cosmic ray pressure between the front side of the cloud and the back side of the cloud. And that pressure jump can actually impart momentum to the cloud and set it moving. It's very important to calculate the magnitude of that pressure jump accurately. And so Chad Bustard did a set of one-dimensional simulations which he showed that you really need about 10 10 grid points in the interface between the cloud and the intercloud medium to really get a converged result. So here, looks like there's this really big pressure jump, and here it's smaller within the cloud and then even larger out here. So this is kind of, if we wanted to study this in a picture, say, of galactic winds, we would somehow have to account for this need high resolution. We went to multiple dimensions. This is what happens in clumping medium. We still get these bottlenecks. The field lines become very warped. So we've done this in 3 dimensions. This particular calculation is in 2 dimensions. But bottlenecks do seem to be there, at least in the simulations, and they have some consequences. So the main consequence is that there are these large pressure plateaus. The cosmic ray self-confinement is really very intermittent. You really only get a sharp cosmic ray pressure gradient interfaces between the cloud and the intercloud medium. We're actually studying the thermal structure of these interfaces. You push on the clumps, but you don't have a general pressure force. But it takes some time to set this up. It takes about an alphane travel time, which implies that self-confinement is kind of time dependent, and a very large system like the galaxy cluster that I showed you might not be in a steady state. There's another instability driven by pressure anisotropy. It seems to be too indolent to really replace the streaming. Okay, so I hope that all this has convinced you that cosmic rays really have a major role to play in interstellar gas dynamics and also their dynamics. And how this role plays out depends on the transport. So it's very important to get this right. Because cosmic rays are nearly isotropic, because it's hard to imagine dealing with this huge range of scales in any other way, we really need a fluid theory, and we have the possibility of creating one, but we should really be informed to a more complete theory of turbulence, kinetic theory of how cosmic rays interact. Unfortunately, many people are working on this. So the traditional picture of pitch angle scattering by small amplitude, randomly phased waves, it's been worked out at a very complete level, but it may not be the most accurate picture. And so we really need to develop this theory at the same level that we have this theory, so we can put it into fluid code. This is my pitch that you should all work on this, because there are just all these advances: observation theory, simulation. There's just so much to do, and I welcome your questions, but I hope you also take the opportunity to talk to the other people here in this program, including the early career people whose work I highlighted. So thank you.
Thanks, Ellen, for what you thought. We have 10 minutes for questions, so like promise of it.
Thank you so much for a very nice talk. I wonder, so you mentioned that the diffusion is transferring how fast. Even the larger density and smaller alpha speed, it can be more turbulent, right? It's super authentic turbulent. And then the cosmic ray, they just follow this suddenly things we may have smaller diffusion, and also suggest kind of like consistent with observation suggest, right? The diffusion they surprise in molecular class. So could you comment on that?
Yeah. So so I completely agree with you that galactic magnetic field lines, if we take out the small scale turbulence, they're not completely straight. They have a complex topology. I suppose it's possible that the magnetic field is so tangled that just field line random walk would that it would still confine the cosmic rays for 10 million years. but that would somewhat surprise me. And I guess I don't know how you would get the energy dependence of the confinement time out of it, although hopping to other field lines we would definitely work. I think if I understood your question, I think the low ionization fraction gas is kind of a problem for any theory, because no matter where the waves come from, there are strong losses. And also, it's not clear that the field is really weak enough to be completely tangled. Some of these polarization maps of molecular clouds are, I realize they're subject to interpretation, but they indicate some degree of order. So you're working on this. I actually have a question for you, but this is probably not the time for it. It has to do with this turbulent damping. It's very interesting. Thank you. So let's talk later.
So what advances in observations are you particularly looking forward to?
So I think that the X-rays will allow us to map hot gas better in galaxy clusters. We were present yesterday at this great discussion section, this contribution from Dasunki Guy, which I think will really help us get at this question of how cosmic rays are confined in radio bubbles, and that in turn will tell us about how they interact with structures, density structures. That's just a couple. And then observations of galactic wind and observations of the circumgalactic medium. Think absorption spectroscopy, that we can really pin down the temperature and density distributions of the circumgalactic medium and characterize the turbulence and the velocity field within it. So one of the predictions of this bottleneck theory is that these clouds are very overpressured in cosmic rays. So I would love to know if that's right.
Okay. Thank you for this talk. Can you maybe explain again why this loop, this Parker bubbles, these bubbles that you showed don't work so well when you have cosmic ray streaming? Why did they?
You get the same thing, but you have to wait longer. Okay. And I think it's because there's a very heavy, this particular simulation, there's a lot of gas above that bubble, and in the diffusion picture you do get enough cosmic rays kind of running out ahead that they can push the gas out and make it more buoyant. So it's just I think if we added some diffusion and some streaming, you would see there would be a continuum. Something that we found that was very important is doing it in 3 dimensions, because in 3 dimensions, the lines overhead can slip by. Otherwise, you just have to carry them the whole way. Emily?
First question. I was wondering if you could comment on the long-term potential of the platform, because I would say you can play it with you today a bit more.
Yeah. So actually, that one of the part of the answer to your question is that this is just a box some height, and if we start with a stratification which is stable to Parker instability, then the bubble reaches a certain height, and then it comes back. It doesn't come all the way back, but it kind of finds a new equilibrium that's intermediate to the old one. We start with a system that is Parker unstable. So for those who haven't heard of Parker's instability, it's basically very close to the Rayleigh-Taylor instability, so heavy fluid on top supported by light fluid is unstable. And in this case, we can kind of regard the magnetic field in cosmic rays as the light fluid, even though they're mixed, with the thermal gas. the free energy source is material held above its natural scale height. And in that case, if it's Parker unstable, apparently we've just given it a nonlinear kick and it keeps going. It's going out of the box. You actually lose quite a lot of mass. But it takes a couple 100 billion years for it to happen. Right?
Yeah, thanks for the talk, Ellen. It was fun, and I hope that the machine learning folks learned about all the advanced models that we're working on that maybe we'll get to use machine learning on in the future once we...
What are your hopes for the black hole entropy people?
Keep question.
Yeah, I didn't mean to deflect you from your question.
My question for you was, could you elaborate a little bit more on what you find promising about the MHD pick simulations? I think that they're interesting too, but I'm curious about yours.
Yeah. So as I understand it, it offers the possibility of capturing kinetic effects driven by cosmic rays without having to also capture kinetic effects for thermal particles, because there's such a huge, so, you know, the so-called traditional hybrid simulations where the electrons are fluid and the ions are kinetic, that gets at the tremendous difference between the length and time scales of the low mass electrons and the high mass ions. Now, the thermal, you know, as you know, the cosmic ray gyroradius is 3 or 4 orders of magnitude greater than the gyroradius of a thermal particle. So, and the same disparity in the gyro periods. So, you know, you don't have to resolve that very fine scale behavior with MHD. Isabel?
Yeah, thank you very much. For the bottom layers, you have a configuration which impulses the process because you are spreading cosmic rays directly at the cloud interface. I wonder if that would be okay in the wind, because then gas is trained and the cosmic ray source is a bit down in the galaxy, and so up they see a net flux, vertical flux. But what about closer to the inner disk?
Yeah.
Numbers would be perhaps more isotropized. Not sure, because they're supposed to follow the field.
So I think so I could interpret your question in 2 ways. One of them is whether the sources of cosmic rays thread, cold, or magnetic field lines from the sources of cosmic rays thread cold molecular gas. And it seems like to some extent they do, because there are these gamma ray observations where the molecular gas in the vicinity of at least one supernova remnant, it's really lit up like a Christmas tree. Maybe you were not taking full ownership of that. It's my impression from looking at the pictures. So it seems like there is some penetration of cosmic rays into molecular clouds. There's also, so I don't know what you think about this, but my understanding, not my own work, but work I've heard about from other people, is that if you take the Voyager cosmic ray spectrum and you ask what is the ionization rate it predicts in molecular clouds, it's too low. It's too low. So it seems like even assuming that the cosmic rays get in there into those clouds, it does. So I don't know. I think it's, I would love to be able to pin down the magnetic topology on that level. Now, as to whether there's a balance of sources, I think that's a good question too. I mean, if there's one supernova every 50 years and they actively accelerate cosmic rays for a few thousand years, sources, I think the chances of having sources in exact balance, not that great. I think there probably is, in addition to the general galactic gradient, I think there probably is always some kind of local gradient, some level.